Hello everyone, my name is Ruth Akintunde, presenting data-informed curriculum sequences for a curriculum integrated game. One motivation for this study is an article by Harrington in 2016, which shows that many adults have been traumatized by mathematics, and one way to alleviate this is by introducing math games and puzzles to children as early as kindergarten. However, a math game with a curriculum sequence that does not teach math skills in a hierarchical manner is counterproductive. Furthermore, this research infers an optimal curricular sequence which promotes effective learning experiences by suggesting prerequisite objectives to students earlier in the sequence. In this paper, we improved learning on a math game called Spatial Temporal Math using machine learning techniques. STMath is a curriculum integrated math game that acts as a year-long supplemental program to the existing math curriculum in elementary classrooms. The game is designed to enhance students' K-12 math skills through spatial visual representation and informative feedback. STMath content is divided by grade level and aligned to relevant common core. STMath is currently being used by over 1.2 million students and 56,000 teachers in 48 states across the country. STMath objectives are broader mathematical concepts, puzzles are contained in levels, levels are contained in games, and games that teach related math concepts are contained in objectives. The data used for this study was collected from 2017 STMath gameplay by third graders from 5 US districts during the 2017-2018 school year. The third grade curriculum contains 32 objectives in total. However, for this study, our focus is on the first 15 objectives. STMath objectives are known as broader mathematical concepts or topics in the mathematics curriculum. STMath objectives can be divided into two categories, default and optional. STMath students start the game with a series of introductory games found under the Fluency tab. Students are then routed to the first objective of their assigned content. Before engaging in puzzles within each objective, students must complete what we call a pretest. This particular pretest or pre-quiz contains 5 questions. After taking the pretest, the student can then start the first level of a game in the first objective. The students need to pass all the levels under a game to pass that objective. Games typify scenarios that apply a particular mathematical concept, in this case multiplication. This game involves finding the right number of boots for X animals with Y legs. Students apply mathematical knowledge to solve puzzles relevant to each objective's content. As students pass each level within an objective, they are exposed to increasingly difficult content under the umbrella of that same concept. At the beginning of a level attempt, the students are given 2 lives. When students fail to complete a puzzle accurately, they lose a life. To pass a level, the student needs to complete all the puzzles under that level without losing both of their lives. On completion of an objective, the students participate in a post-test as a prerequisite to proceed to the next objective. In this study, we analyzed gameplay data by third graders in 5 US districts during the 2017-2018 school year. Let us first define some important concepts. Retries are level attempts other than the first attempt that occur before the student passes the level. Retries are different from replays in STMath. Replays on a level are all attempts that occur after the student passes the level. So many retries indicate a lack of understanding of a concept. Therefore, reduction in retries indicates a reduction in the difficulty of objectives. We will now review some related work. Shen and colleagues introduced the combined student modeling and prerequisite discovery, the command algorithm, which uses Bayesian networks to learn prerequisite structure of skills. Their work generates prerequisite graphs of mathematics skills. Shen et al. In 2015 discovered prerequisite structure of skills by using association rule mining on a large student performance database. Ruth et al. In their book titled In Order to Learn, How the Sequence of Topics Influences Learning, extensively explained that the order of representation or presentation of materials influences the speed of learning as well as what is learned. Different orders of presenting materials can lead to different learning outcomes. These differences occur in both natural and artificial learning systems. Doherty et al. In 2016 introduced SCOVA, which is sequencing constraint violation analysis, which provides a method for evaluating sequencing constraints and how they impact post-test performance. Our approach to curricular sequencing, however, produces a partially ordered sequence which is driven by students' retry behavior. Inferring prerequisite structure of a mathematics curriculum by evaluating its impact on the number of retries is yet to be explored. We conducted a preliminary analysis to discover the sequence of STMath objectives played by elementary school students in 5 US districts. This figure is a sample from our dataset. It shows a bar chart of the sequence with which 5 districts, namely districts A, B, C, D, and E, played 5 STMath objectives. The number in each bar represents the position of each of the 5 objectives in the curriculum of each district. Note that District B did not place value bundles, tens, and hundreds, and District A did not play concepts of area and perimeter. From analyzing this sample data, we can see an important pattern, that the rise and fall in the number of retries needed before passing some objectives co-occurs with the position of such objectives in the curriculum sequence. Using this pattern, we categorize the objectives into 3 major groups. Group 1 objectives are difficult, that is, they have a high number of retries, or easy, that is, they have a low number of retries, depending on their position in the curriculum sequence. While Group Group 2 objective have a low number of retries no matter their position in the sequence. Group 3 objectives have a high number of retries no matter their position in the sequence. From the plot, we can see that two objectives, namely place value bundles, tens and hundreds, and number patterns, fall into the first group because their percentage retries dropped when played later in the sequence. Let us now closely examine the first objective. Place value bundles, tens and hundreds. When played earlier as the second objective by students in District A, it recorded about 9% retries. This means it was more difficult. Whereas when that same objective was played as the 14th objective in the sequence by District D, it recorded about 3% retries. This means it was easier, and students in District D must have obtained prerequisite skills from the 1st to 13th objective before working on this objective. From the plot above, multiplication concepts and division concepts fall into Group 2 because they are easy no matter the order they were played. We believe that these objectives are already well placed, so their current order should be maintained. We suggest that some of these objectives should be played at the beginning of the sequence to help the students become more familiar with the game environment. Concepts of area and perimeter falls into Group 3. From our analysis, we discovered that some game mechanic reasons for this, such as the potential lack of intuitiveness of the game. We suggest that the game should be redesigned. Note that we have made suggestions for playing objectives in Group 2 and 3. We are left with Group 1 objectives. To do this, we highlighted some research questions. 1. Can we use data to infer curriculum sequence that places prerequisite objectives first and teach math skills in a hierarchical manner? 2. Do objectives currently played before each goal objective predict the goal objective? That is, does the current curriculum sequence place all prerequisite objectives first? These research questions can be answered in 3 major steps. But first, let's see what the existing curriculum looks like. The order in which estimate objectives are played is different across districts, classrooms, and students. Students in the same school might not play the game using the same curriculum sequence. Teachers have the freedom to assign different objectives to different groups of students in the classroom at a particular time. Although prior research by Liu et al. In 2019 suggests that not all teachers do this. Instead, most often, reordering is at the district level. Therefore, we extracted the largest number of students that played the first n objectives in the same sequence. An objective, for example, y, is considered ordered prior to another objective x if the majority of its gameplay happened prior to the completion of the other objective. For example, we consider y as ordered before x if a student attempted the first level of objective x and was switched by the teacher to objective y, completed all levels in objective y, and only then completed the rest of the levels in objective x. In this situation, we say that most of the gameplay in y happened before x. In the first step, we performed some exploratory data analysis. The third grade curriculum contains 32 objectives in total. This table shows the highest number of students that completed the first n objectives in the same order for each districts A, B, C, D, and E. Our aim is to analyze data from students in the same districts that completed n objectives in the same order. From the table, we can see that as n increases, the number of students reduces. For this study, we selected the column where n equals 15. This represents a trade-off between the number of objectives and the size of the dataset. That is, the number of observations of students involved in the study. Our dataset therefore contains 826 students from District A, 1826 students from District B, 376 students from District C, and 137 students from District D, and finally 163 students from District E. Thus, we observe the way a total of 3,328 students from the 5 districts play the first 15 objectives. In the second step, we replicated the 2017 study by Liu et al. That introduced a novel data-informed method to determine pairwise orderings for objectives in the curricular sequence. Liu et al. Performed this study on 1 district. This work implements this study on 5 US districts and also validates this study by Liu et al. Using students' retrial behavior. But first, let's define some more important concepts. We define objective performance for each student as the average of first attempt performance on all levels in an objective. Suppose an objective has 20 levels. The performance of a student in that objective is the average of the first attempt performance on all 20 levels. To get the district performance on an objective, we take the average of all students' performance for that objective in that district. We use the first attempt performance as this provides information on student skills regarding the level content before they experience any feedback. Thus, first attempt performance on a level shows how much prerequisite knowledge a student has acquired from other objectives before playing the current objective, and subsequent attempts may not truly reflect each student's knowledge of the mathematics concept. We now define goal objective as each of the first 15 objectives in the curriculum. This study uses mixed effect regression to know what objective significantly predicts performance in another objective. Potential predictors of the goal objectives are all objectives that are played before the goal objective. For example, suppose number pattern is an objective in the curriculum and it occurs as the 7th objective. The first 6 objectives are all potential objectives, while number patterns is the goal objective. We perform pairwise Spearman correlation on all 15 objectives, resulting in 210 correlations. Next, we found the average of the correlation table, which we'll call mean core, and filtered out objective pairs with correlation value less than the mean core. Next, we used mixed effect regression to find what objectives are significant predictors of the goal objective. Linear mixed effects models are mixed models used for regression analysis involving both fixed and random effects. These models are an extension of linear regression models such that the linear predictor contains random effects in addition to the usual fixed effects. Linear mixed effects regression allows us to evaluate the significance of fixed effects in created models. Fixed effects are the independent variables recorded for each observation. Random effects are additional variables and specific groups which are objectives, which are observations can fall into. For example, students in each district belong to different classrooms, and so we use classroom as a random effect. The mixed ML function in Python in particular provides us with the p-value of each fixed effect variable. This is necessary for our analysis because our aim is to see which objectives are significant predictors of the goal objective. A predictor objective with p-value less than the threshold, which is 0.05, is a significant predictor of the goal objective. To construct a linear mixed effect model, we extracted all the objectives played before each goal objective. These serve as potential predictors, also known as fixed effects, of the goal objectives as shown in the equation above. Fixed effects are PL1 to PLK, which represents the student's objective performance multiplied by number of levels the students completed for objectives I equals to 1 to K played before the goal objective. Note that performance on the ith objective is the average first attempt performance on the levels in that objective completed by the students. And position O of the goal objective is the current curriculum sequence. In the current curriculum sequence as fixed effects, whilst classroom C factor is used as random effect. Therefore, we construct the above linear mixed effect model. We predict PL, where PL is a student's performance on the goal objective multiplied by the number of levels of that objective completed by the student. Predictor objectives that have significant p-values were marked as good predictors, while the rest were not considered as predictors. This is how we detected significant predictors of the goal objective. In addition, only predictor goal objective pairs that had correlation greater than the mean score were included in the analysis. A total of 58 predictor objectives were found to be statistically significant for the 15 goal objectives. To answer our research question, not all potential objectives in the current curriculum predicted the goal objectives, and in fact, some non-potential objective predicted the goal objective. Now we define dark red tiles. If any one district orders objective X before Y, as in XY, but X does not predict Y, and another district uses YX and Y predicts X, then that relationship is shown as a dark red tile, and objective Y should be played before objective X. We will label this scenario with a dark red tile in the following figure. Dark red tiles generally suggest a revision of the order of objectives involved. For example, the suggestion that multiplication, MULT, should come after multiplication and division relationship is a dark red tile. In other words, the ordering YX results in better student performance on X and suggests that Y should come before X. Dark red tiles were found by checking 5 different districts that played estimates with different curriculum sequences. In addition to replicating the Liu et al. Study across 5 districts, we also associated the suggested orderings with the number of retries. Therefore, the third and final step involves deriving a partial ordering of objectives and evaluating the suggested orderings to observe if the number of objective retries was reduced in cases where students already followed our suggested data-informed sequence. A partial order is a binary relation less than over a set S satisfying the following axioms. For this study, note that the relation less than means should be played before. The order S is transitive. If I is played before J is contained in S and J played before I is contained in S, then I played before L is contained in S for all I not equal to J not equal to L. We can go ahead and interpret the subsequent statements. After separating the group 2 and 3 objectives, we use the dark red tiles to create a binary partial order between the dark red tiles that involved group 1 objectives and their prerequisite objectives. Therefore, from the figure shown, it is suggested that round 3DGT, which stands for rounding 3-digit numbers, and mult and div_s, which stands for multiplication and division situations, should come before SO1P, which stands for place value bundles, tens and hundreds. And they should also come before SO3M, which stands for number patterns. One reason for this could be that round 3DGT teaches students the concept of nearest whole numbers and the puzzle environment for mult and div_s is quite similar to that of SO3M. This most likely prepares the students for success in SO3M. Also, prerequisites for multiplication MULT includes SO1Y, addition and subtraction with regrouping, and mult and div relationships. The suggested partial orderings were found to reduce the rate of retries of objectives in the partial order shown in the figure. We recorded an anomalous relationship from our results, and this is represented by the red dotted lines. We discovered that when SO1F and mult and div_s are played before SO3M, SO3M becomes easier. But if it's the other way around, it becomes difficult. So although one red tile suggests this order, we do not accept it because it does not contribute to our goal of reducing the number of retries. We use the inference from our replication study to suggest a partial order for objectives in group 1 based on the predictive abilities of objectives. The sequence of earlier to later objectives goes from left to right. Districts that already followed our suggested order recorded a reduced number of retries for group 1 objectives. Limitations to our study includes variation in district implementations of STMath and different instructional methods for administering the math curriculum. For example, some teachers might teach prerequisite skills in class before bringing the students onto the STMath game. Although we made classroom factor a random effect in our prediction analysis to account for classroom effects, future work could gather external SC2 data to understand the impact of gameplay behavior on both class and district-wide outside of STMath curriculum. In conclusion, students gain self-confidence as they perform better and are now equipped with the knowledge from prior objectives which are required to ace later objectives. This kind of student modeling is beneficial to both the serious game and analytics communities. Thank you.